here, right? And let's go back to where we left off. We were discussing this, but we left off on feedback amplifiers, right? So the next topic down the road is on precision rectifiers. So I'll go through that. We already discussed part of this when we were looking over the last exam paper, the December paper. So let me get up the slide here. So the topic today is on precision rectifiers, and that particular topic was under the applications for operational amplifiers. Okay, so I'll share that one, which is this here. Okay, so on this, before we look at the question, we already addressed, and we saw the only difference between that question and the one that I gave you all in December was that the diode directions had been reversed. And that just means that the diodes, the opposite diodes, what would have biased the diode on in that version would turn it off now. Okay. Okay, so the idea behind it, just in general, is that if you're trying to rectify signals, and you remember what rectification is, or why we would want to do that, is that if you have a signal, sometimes in order to see what the signal is doing, what you're more interested in is the sort of positive amplitude of the signal, or maybe the average value of the signal. And either way, the way to get that is to rectify the signal, because most of the signals that we deal with would be bipolar signals. And what you are interested in might be either the peak value here or the peak value here to address some situation, as if to work as you're trying to detect some anomaly and so on. The issue is that most times when we rectify, the device that we use to rectify is a normal diode. And the diode works good in that it lets current go in one direction and it blocks it if the diode is reverse biased. The disadvantage of this, of course, is that the diode doesn't turn on until the bias voltage is about 0.7 volts, right? It varies a little bit from diode to diode. And in fact, some diodes may turn on or start turning on as low as 0.4 volts. And then some of the power diodes, which you will meet if you do things, they course power electronics. There are some power diodes that typically, because of how they're constructed, typically they need about like 1.5 to almost 2 volts to turn on. In either of those cases, what happens is that very small voltages, if you have voltages of 0.3, 0.2 volts and so on, and you want to rectify them, then you can't use a diode. Of course, what you can do, one way around it, of course, is if you have a small signal, you can put an amplifier and then do the rectification, after, right? But so instead of doing that, what we do is to basically figure out, okay, I have an amplifier, I have to design an amplifier and then go about and either put up a rectifier circuit and so on, and then go and process there. What I can do is to make use of some of the characteristics of an op-amp and combine the two of them. And if I combine the two of them, then I create a device, a unit that is able to rectify voltages less than the typical turn-on voltage of a diode. And what the amplifier basically does is that because of the behavior of the amplifier, once you put the diodes in the feedback loop of an op-amp, the op-amp biases the diode sufficiently on to get it working, and then the rest of the diode, the rest of the circuit works around that. That's the beauty about the op-amp. Okay, that particular thing, of course, we call a precision rectifier, and it behaves as close to an ideal diode as you can get. So the ideal diode means that you don't need any turn-on voltage. As soon as the voltage crosses zero, either positively or negatively, depending on how you wire it up, the thing starts to conduct. One configuration we saw was this particular one that we saw in the exam, where you take a normal inverting amplifier, and in the amplifier itself, so the two resistors here, if you ignore the diodes, is a normal inverting amplifier. And what we do is that we add these two diodes in this configuration here. And as we saw, what happens is that if here is negative, because it's an inverting amplifier, it turns here on positive, right? Then a positive bias here will turn this diode on, but reverse bias this diode. And once it turns on, it means for a negative input, the output is going to respond here. When you put a negative input, or when you put a positive input here, because it's an inverting amplifier, here goes negative. Negative will turn off this diode, but turn on this. And what the amplifier does, remember the op-amp tries to make these two voltages equal. So it is trying to pull here to ground. Here's positive, is pulling here to ground. And the circuit behavior, if this is pulled to ground, here goes to just about minus 0.7 volts, just enough to turn on this diode here. So the op-amp is doing the turn on behavior for you. And then after that, the rest of the circuit, it doesn't matter. The op-amp, the instant you put a little voltage on here, in this case, a little positive voltage, the output here immediately tries to go low. It will try to go low by the gain of the op-amp. And as soon as it goes negative, this diode turns on and forward biases sorry, here goes negative, forward biases the diode. Because here is trying to keep to zero, the op-amp, in order to keep the diode going, the op-amp drops here to just about 0.7 volts and keeps the diode on. And then as far as that is concerned now, you could treat this as a short circuit and this as an open circuit. All right? If you reverse the direction of the diodes, then, which is what the question, the past paper question is asking, then the polarity of the output changes, okay? So, and we have the explanation here. There are a couple of variations of it, and this one, I'm showing here where when I took out the diode, what happens and so on, right? This particular one was an inverting linear half-wave rectifier. So it's inverting, and this was the one in the exam. So if the input is looking like this, if the input, where am I? If the input, right, if my input is looking like this, then the output, because it's inverting, right, you get nothing for the positive. Here, when it goes negative, you get an output, right? So the output is going to look something like that. Right? A variation of that, one other type of device is something called a polarity separator. And this one works nice in that depending on the polarity here, one of these two outputs is active. And you could figure it out for yourself. I'll kind of leave that and then for you to do, because it's very easy. This is an inverting amplifier. So remember, if here goes positive, what the amplifier will try to do. And if it goes negative, what the amplifier will try to do. So this is the kind of things that if you have a signal looking like this, right, then what's going to happen is that on one of the outputs on both of the outputs, you're going to get an output, but you're going to get either the lower half or the upper half. So you can use it accordingly, depending on what you're looking for. All right. It's a polarity separator. It's a type of precision rectifier because these amplitudes here can be less than 0.7 volts. All right. This now was another type of one, precision rectifier, and this one now is you're connecting the input to the non-inverting input of the op-amp. Remember, in an op-amp, the non-inverting input has this high input impedance. It has a higher input impedance than the inverting. The inverting the input, if you were to go back here, right? Remember, because of the virtual earth behavior, here is essentially ground, so that a signal coming in sees an input impedance of just R. Right? Typical op-amp, usually we have like, this might be like if it is a normal op-amp, these might be like 10K resistors. So the input impedance for this will be 10K, which is quite low. Right? So when you send it to the non-inverting input, remember now, because of the characteristics of the op-amp, although here's now the earth point, but here now you're trying to match the input voltages here. So what is happening is that the input impedance is actually seeing whatever is the input impedance of the op-amp, which typically is a fairly large value. Right? This now tends to run into the megohm side. So it's not fully dependent on the resistors here, but what you're seeing coming in there will be in the megohm sort of range. Okay. So how does this one work? Well, again, we back to using the two diodes, and it depends on the polarity of the input. If V is positive, then because it is a non-inverting, if here is positive, then the amplifier is going to give a positive output. If point A is positive, then this diode is on and this diode is off. All right? And then now the rest now is, look at what happens. So it comes on, I put the input here. Now, DP is conducting, and the inverting inputs of both op-amps are at Vn, right? So here's positive, and here's positive. Notice that the input is connected. Of course, here we have two. This particular rectifier has two op-amps. The previous one had just one. And then now you could see what the current flow is around here. If here, where's my pointer? If here is V positive, right, then the current coming through here is going to be Vn over R. All right, but here's Vn. This is an inverting amplifier, so here's Vn. So if that is the case, then, and this diode is off, right? It means this point here is disconnected, so that you have no current flow going through these points at all. Right? So the only output is as a result of this amplifier here. So we have a positive output coming here. Yeah? Dn, because we have no connection between the output of the op-amp, since Dn is out, we have no connection between the output of the op-amp and these resistors. Right? And again, if you want so Vn, of course, here, of course, electronically, if you were to model it, here would, to keep DP on, here would actually be about 0.7, right? So it's biasing this on. Dn is off, so this bit is out of the circuit. So there's no connection between point A and the rest of the circuit. if there's no connection between here, then we have no, this point is not connected to any voltage here. And if the output here, because of the op-amp behavior here becomes positive, then if here is V in, right, and here is V in, then there's no voltage drop across these resistors here, right? So there's no current flow. Okay, so the output when V in is positive, V out is positive. When V in is negative now, when V in is negative, so we put a negative voltage here, right? So we have negative voltage here. Let's not get rid of that. We have negative voltage here. So the current coming, if here is positive and here is negative, we're going to have a current flowing. Here's more positive, here's ground, sorry, and here's negative. We're going to have a current flowing here, right? And the difference, the current now is minus V in over R, because this is minus V in, right? So if the current is going here, then here's negative. So here's negative because a non-inverting amplifier. So this guy is off. And this guy is on, so we have a short circuit connecting here. So it means that point A, right? Look what happens now. So point A is negative. The current of the op-amp, remember the current flow of the op-amp now will be in this direction, so that this point here is going to be minus 2V in. Yeah? Here is at minus V in. So here is at minus V in. Yeah? So that the current going in here, so here's a little bit more positive. So we have current coming this way now. What is the current? The current is V in over R, but that is passing through a resistor of 2R. So therefore the voltage on this side is going to be plus 2V in here.
So
yeah,
when DN is in reverse bias, right? That acting like a short circuit.
No, when DN is reverse bias.
Yeah.
If DN is reverse bias, that is this one. If DN is reverse bias, I mean I have a positive here and a negative here. That is out of the circuit, right? So in other words, this here, this is an open circuit. If this is reverse bias, it means like I've opened up this line. You remember reverse bias diode mean no current can flow. So for all intents and purposes, I don't have this connection anymore. When it's an open, a reverse bias diode is an open circuit. A forward bias diode is a short circuit. Look at it like that.
Oh, okay.
Right? So in this case, this is a short circuit, so DP is out, right? I don't have a fat pen here, but what happens if I put that there, then DP, where's DP? Where's my pointer? Kind of hard to say why, right? So this was happening here. Right, in this case, so DP is out of the circuit and DN is in the circuit now. Right, so DN, right, so this is just now. Right, so DN is in, so ignore the diode and you basically have a connection, a short circuit connection between those 2 points. All right. So then,
sir,
yeah,
just a quick question. How did you get the minus 2 VN? Is that like is it because it is twice the voltage drop or something?
The minus here, yeah, well, look what happens here. So we have, let me just try to get back this point. It keeps disappearing on me. So here, remember V in is negative. So I have minus V in here, right? Remember the current flow into the op-amp is 0. So we have a current flowing here, that is minus V in over R, nothing is flowing into the op amp, so that current is now going this way. So therefore, I'm going to get another Vn being dropped across here. The only way, if the current is going through here, is minus V in over R in, and I pass it through a resistor R, it means that the voltage drop across this is going to be minus V in. So if this is the drop across here is minus V in, and here is minus V in because of the virtual earth behavior, then this point here will have to be at minus 2 V in. Yeah?
Okay, thank you, sir.
All right. And then we're going back here now. So that here's at this point here is at minus 2 V in. Here is at minus V in. So that the current flow here is more positive than here. So the current flow is going to be in this direction, nothing coming into the op amp. And this current now has to come back out from the output of the op amp. So the voltage drop across this resistor now. So again, the current here is V in over R. And I am multiplying it by a resistance of 2R, so that the voltage drop across here is 2 V in. So if here is at minus V in and the voltage drop across here is 2 V in, then plus 2 V in, then here has to be at a voltage of plus V in. Yeah? So in other words, the output again is positive. But for the first part, when Vn was, for this one, when Vn was positive, when Vi was positive, the output here was whatever Vi was, right? So Vi positive, the output here is also positive. When Vi is negative, when Vi is negative, the output here is positive still. So if you combine the two of them, regardless of what the input is doing, the output is going to be giving me this behavior. When Vn is negative, when Vn is positive, we get a positive output. When Vn is negative, we get a positive output. So this is in fact a full wave rectifier behavior, right? And in fact, we call this particular type of rectifier by first off adding the second amplifier and using them in the non-inverting mode. For both of them, what we have created is a full wave rectifier. Because we're using them in a non-inverting mode, as I said, the input impedance is now high. So we've created a high impedance full wave rectifier. The previous one that we had here, the single op amp one, is an inverting half wave rectifier, but the input impedance is low. It would be limited to whatever this value is. You can increase the value. Typically, the op amps will tolerate maybe a value up to about a megohm, right? And that's about the sort of limit that most one of them. What I have 1 megohm, right? Which is about the limit of the size of these resistors that you can use with typical commercial amplifiers that you would get. Beyond that, the current flow in these circuits starts to get close to what the amplifier, although we say it doesn't take any current, the real commercial amplifiers take a very few microamps here, right? The better ones take a couple of nanoamps. The really, really good ones take picoamps. But normally, if you're dealing with like the 741 general purpose amps that you've met before, the input current here is in the order of a few microamps. So from the time you start to put the feedback on input resistor, in the order of a megohm, it means that the current flow inside of these lines tend to be equal to the current, tend to get in the same sort of ballpark as the current that the amplifier is really taking. So it doesn't work too good after that, right? Usually we try not to go more than about 100K here. And if you want gains and so on, this typically is about, if you're using 100K here, this will typically be like about a 10 to 100 to 100K, right? So you're not getting that much input impedance, but this version now, because inherently, because of the circuit design of most op-amps, even a 741 op-amp, the non-inverting input impedance is already bigger than 1 megohm, right? And the better op-amps, they were the ones that, for instance, use JFETs, right? Tend to have or MOSFET inputs and so on, tend to have huge input impedances, which are in the order of 10 megohms to the gigohm sort of bracket, right? So this one now, we start to use the non-inverting input, so the input impedance has gone up. And then secondly, by sticking in a second op-amp emitter here, we are able to get the full wave rectifier behavior, whereas before we got the half wave. Okay, so this particular one gives you full wave, and if you simulate the circuit, right, this is sort of the typical waveforms that you would get. The red one, of course, being the input, the sinusoidal input to be rectified coming in, and the output now, of course, is the green line. There is a little bit of, well, they're on different axes here, so you can't see if there's a gain or not, all right? But typically, that sort of amplitude here, this sort of peak-to-peak amplitude here, remember, it's a precision rectifier, so this thing can be less than 0.7 volts peak-to-peak, all right? So you're able to rectify, like I mentioned before, things like biomedical signals, when you're trying to amplify signals from skin contact for like heart measurement and those kind of brainwave measurements and so on. You're generally dealing with extremely small signals inside of it. All right. So any questions? I wouldn't be discussing anything more than that today. All right, because I have to go on sort of something for the department. But any questions on how these things, how it operates, right? As somebody was mentioning before, just remember that behavior of the diode. If the diode is forward bias, right, then you could replace the diode by a line. If the diode is reverse bias, then this is what you have. You have an open circuit, right? This is a short circuit here. This is an open circuit here. And once that is there, once the diode is biased or reverse biased, then you could basically ignore the diode from the circuit and just analyze the circuit as though you have straight wire connections. As I mentioned in classes, like a valve, it's either it's on or it's off. The amplifier, the op-amp, makes sure that the diode is biased fully on or totally reverse biased. So you're safe to assume, like when this one is off, that we have absolutely no connection in the feedback loop here, right? So you could even redraw the circuit as though it didn't have a diode in it, right? So you have the resistor coming in here, right? And then the resistor going forward here. And what we have is this, right? So ignore the diode. This is what the circuit looks like. So you have R here, and then you go back up, and draw the rest of the circuit here. All right? And then the behavior is normal. As I say, all you really have to do after that is to figure out how an inverting and a non-inverting amplifier works. So you draw the circuit without the diodes in it, and just follow the voltages and the currents. Here's grounded. All right.
So I have a question, right? How could you have VN on the output and then 2 VN? Positive 2 VN.
This here,
Yeah.
this is the voltage drop across here, not the output. The voltage drop across here is 2 VN, right? Because of the current flow. So the current flow is creating a voltage drop of 2 VN across this. So if here's at minus VN and this has a voltage drop of plus 2 VN, it means that the output here is going to be at VN, right? That red line. Somebody asked me a question at the point when I drew it, so I didn't put it out. This 2 VN is supposed to be the voltage drop across our flow, right?
Okay.
Yeah. Fair enough.
But if the voltage flowing like from the output, right? Would it need to be the total voltage drop, like equal to the total voltage drop?
I'm not too sure what you're getting at.
I was just like asking, like if the voltage that supplying the voltage drop, if it needs to be equal to the total voltage drop, so the voltage at the output needs to equal to the total voltage drop through all the resistors.
No. What happened is that look at where the current flow is. Here is grounded. Here is at plus VN. Sorry, here's at minus VN. So here's minus VN. Right? Here's at minus VN. So that the current flow for this, there are two op amps working inside of here, right? Because here's at minus VN, I'm not taking any current in order for the current to flow, here's minus, it means here the ground is more positive, so the current going this way, right?
Yeah.
So in order for the current to go that way, this point here has to be at minus 2 VN. The op amp itself now, the current from the op amp is not taking any current coming in here. So that in order for the current to continue to flow, right, the voltage drops across this chain. Remember we putting minus V in here, right, because of this thing. So in order for the current flow to work like we have it here, we have the current going this way, and the output of the amplifier is biasing in such a way, shouldn't have this out thing, is biasing in such a way to send current back to create here a voltage of minus Vn. This is not taking any current, so the only way that could happen is if here is more positive than here, here is more positive than here, so the currents actually cancel at that point in time. If you were to do the math, the currents actually cancel, right? But it's creating, in order for that to happen, here has to be at plus Vn. Right?
I see it. It's a bit confusing, to be honest.
Okay. Do what I was saying. Well, draw it over as, let me see, just let me see if I do that here. And let's draw it now as though, so we have the two op amps here, positive. Right, we have ground, right, we have one resistor, two resistors, three resistors coming on the output here, right, connected here, here is connected here, right? So we have V in here, right? So that is what it is when Vn is negative. Right? Forget the diodes. This is the behavior now. Because Vn is negative, this diode is now biased. So if you look at it here now, right, here's minus V in. So this point is minus V in. This is resistor R, this is R, this is 2R, and that's the key here. This is 2R, this is R. So if this is minus V in, all right, if this is minus V in, what is the current flow? We have nothing inside of here. So what is the voltage? The current through this resistor will be minus V in over R. And since that current can't go into the op amp because the op amp is taking nothing, that is going through these two resistors here.
Yeah.
Right? Good. Here now, we put another minus V in here. So you put another minus V in inside of here. This is an inverting amplifier here. So if I put a minus V in inside of here, the op amp now is going to try to supply current to keep this, because of the virtual behavior, is going to maintain that. In other words, it has to supply some current to keep this at minus V in. And that current has to, the current has to be equal to whatever the rest of the circuit is handling. So as I was saying, we have minus, what do you call it? We have minus V, oops, minus, that is out of the way. Hold on, I have something coming up on my screen here. Where am I? Right. So the current coming in here is minus V. I'll just use V over R. So that's going through here, right? If minus V over R is going through here, it means that this point is going to be, has to be, if here's minus V in, then here has to be minus 2V, right? Here's V in, here's minus V in, all right? So here's more positive than so at this point in time, now we have, let me see how best, trying to describe it with current flow is a little bit odd, but let me see how best I can do that. The current here is more positive than this point. So the current is doing this, right, for the op amp. At this point in time now, we have minus 2V in and we have minus V in here. So in other words, the current flowing this way, right, from this point now, because here is more positive than here, is going to be minus V in over R. So if the current flowing this way now through here, this is not taking any, so that current has to come from here. So minus V in over R multiplied by 2R means that the voltage drop across here is 2V. So if the voltage drop across here is 2V, I have minus V in here, all right? So the only way, if here is minus V in and I have a voltage drop of 2 in, here has to be plus V in, right? That's the only way, and this current now is going back this way. So all of this is going in because this diode is on. This is how the current flow is looking like, right?
Okay. When you describe it with current flow, I think, well, I get it. It makes sense.
Right?
Yeah.
Okay. So any other questions?
So when VI is negative, right, you're letting the both inputs be negative.
Yeah, but they tie together. So once this goes negative, remember there's the same point, there's the same connection here. So both of them connected.
Oh.
And when same thing when VI is positive, both of them connected.
So when VI is positive, the both inputs will be positive as well.
Right. Well, what happened here is that the both inputs are positive here, right? But because this diode is off, there's no connection between A and the rest of the circuit. In other words, this current flow is disabled, right? So when Vn is positive, the current flow, this whole part of the circuit more or less is disabled, If Vn is positive, this is a normal inverting, a non-inverting amplifier. So here will be V positive, right? This part of the circuit, because this diode is now out, there's no electrical connection between amplifier A and the rest of the circuit. Right, so everything is basically, in other words, as far as the system is concerned, it just has B, and B is a non-inverting amplifier. So if I put a positive on B, then output just tracks whatever the non-inverting input does. You could draw it out again. If you were to draw it out from here, then this connection here doesn't exist, right? So if that connection doesn't exist, then you could see that the rest of the circuit, you have a ground, so you have a ground here, right? This circuit is disconnected so that you basically could ignore the whole amplifier behavior on that side, and then just look at as though you have two are connected to input B, but this side is grounded. Yeah. So draw it over, do what I was saying, draw it over, and if this is open circuit and this is short circuited, then because this is short circuited here, if Vn is positive, and this is open circuit, then this particular op amp is out of the circuit. Dn being open circuit basically means that there's no electrical connection. I think I had that drawn some. Oops, no. I had that electrical that drawn I believe somewhere. If you right, yeah, if you were to take so take this out, there's no connection here at all, right? And this is a short circuit here. Right? So if you short circuit this and you have no connection inside of here, it means this point is not connected to the circuit. So this op amp just has a floating output. I've drawn the op amp here, and the op amp is this, right? And then I have the other op amp. I have the input coming here, which is plus Vn, right? I have the resistors coming, so I have. But this is if I put V in positive, this is V in positive here, right? So I have a resistance, I have the feedback resistance. So this is what this is looking like here, right? This is not connected, and here is at V in positive, right? So if here is at V in positive, here is at V in positive, right? Essentially, so the op amp will just basically track. If you have this is plus and minus. This is 2R here. Okay. This will just because all of this. Where's my pointer? Where's my? I lost my pointer here. Right, there we are. Right. So let me use this instead. This part of the circuit here, all of these two resistors. Now here's V in positive, here's V in positive. So all of this is essentially these two are now out of the circuit. So you can ignore all of this, and you just have a non-inverting amplifier that I put a V in positive on the non-inverting input, right? No resist. This is out of the circuit, so it doesn't really matter what I have here. The output is just simply going to track the input. It's like a voltage follower at this point in time, because you have no resistance. If you have V in and V in here, it means that there's no current flow on this side at all, right? So you have an amplifier basically like this, positive, negative. If I do this, right, and I have nothing on this side, right? All I have done here, this is like this is an amplifier, an open loop amplifier, basically, right? All I do, if I put a positive here, is going to give me a positive on that side, right? That's all. It's just a voltage follower at that point.
So the voltage at A will be positive.
The voltage at A, no, well, what happened? No, the voltage at A will actually, yeah, the voltage at A will be positive, right? That is why Dn is off. So the instant this goes positive, Dn is reverse bias, so it's off. And what happens? dP goes on, so it keeps this at about 0.7 volts. And by keeping point A at 0.7 volts, it removes Dn from the output. So in other words, this is what you have. The op amp, you have this kind of arrangement here. You have a short circuit between the non-inverting and the output, more or less. The output is holding itself at 0.7 volts, but nothing connecting this op amp to anybody else. It's just floating, so it has no part to play in the circuit. Right? So all of this, the resistance associated with the resistances associated with that op amp are out of the circuit. Op amp B now, right? It has nothing on this side connected. So this just works simply as a voltage follower. You have a resistance in the feedback, nothing in the input to ground. So this is just working as a voltage follower here. Right? So if Vn is positive, you get a positive coming out. When Vn goes negative, if I didn't have anything else here, Vn went negative, then there's a voltage follower. This would go negative. But that is where the second op amp kicks in. Oh, sorry, op amp A kicks in. When Vn goes negative now, it brings Dn into the picture. And by bringing Dn into the picture, we have this circuit being created now, where you have this connection being made. So that op amp A is now in the circuit as well as B. All right? And as it turns out, it still gives me a positive Vn coming out, which is why we get the full wave rectifier behavior here.
Sir, I just have a quick question. So in short, with the whole rectifier being high impedance and the other one being low impedance, is it because of the resistors, or it doesn't have anything to do with that?
That's what I was saying. If you go back to this type of circuit here, right? And inverting, when you have an op amp in the inverting mode, remember input impedance has to do with what the input signal is seeing. In the inverting mode, because of how the op amp is connected, this point here is at ground, right? Because of the virtual earth behavior, this point here is at ground. So here's at ground. So any input signal is just seeing the value of this resistor. Usually in most op amp applications, that is like 10K to maybe 100K max. Right? So the input impedance is limited entirely by the value of R. In the non-inverting mode, right? In turn, what you're seeing here, the input signal sees the input resistance of the op amp. The internal circuitry of the op amp, I don't know if you all ever cover that in level 1. It doesn't matter, but the internal circuitry for this typically has a fairly high input impedance there. There's an input impedance there. The input, in fact, is something like an op amp with an input bias resistor of something like about 1 meg. So that on the non-inverting input, the signals, without anything else, the signals see about 1 megohm for a typical op amp like the 741, right? So in general behavior, once you configure it, for operation, the non-inverting input always has a higher input impedance than the inverting input. Yeah. Why? Because in the inverting amplifier, we ground this input here, and by doing so, we make this point ground, so that any input signal is going to see this resistor as the input impedance that it has to feed, which is typically low. Yeah.
Okay, thank you very much, sir.
All right. Okay, well, we ended up going there full class here. They waiting on me for a meeting, but that's not a problem at all. Okay, so what I will do,